Now that we've looked at how to draw Newman projections and have gotten comfortable with drawing them in their various forms, what we're going to do now is use them to look at free rotation over carbon-carbon bonds, and specifically the energetics of free rotation. So getting into it, what I want to start with is reminding us that Newman projections allow us to see free rotation a little bit more easily than we would if we just had seesaw structures. For example, the first time we looked at the free rotation, a 60-degree free rotation over a carbon-carbon bond, it was a little bit awkward. I was able to do it quickly because I've been doing this for a while, but I'm guessing many of you still don't really know how I got from how I was able to do the free rotation so cleanly, and it's because I've done so many kind of rotations with Newman projections that I'm able to kind of see these things a little bit easier at seesaw structure, with a seesaw structure depiction. So in particular, Newman projections allow us to visualize what things are more and less stable. So in general, eclipse conformations are less stable than staggered conformations, which are in turn more stable. Okay, and that sort of makes sense, right? If you, I mean, just from your own ability to draw these things as Newman projections, when you go from an eclipse conformation to a staggered conformation, a staggered conformation to an eclipse conformation, it's a little bit more difficult to draw that eclipse conformation. It's a little bit uncomfortable. Everything's overlapping. It's not just you. It's these atoms are starting to feel the effects of being near to other atoms. That's one interpretation of it. There's also this sort of stereoelectronic effect. Anyway, let's not get into that now. But this structure on the left, which is staggered, is more stable. The structure on the right is less stable. And we've called these conformations by some important names. We use the term staggered for the structure on the left because the hydrogen atom at the dotted carbon is splitting the hydrogen atoms at the back carbon, and then the atoms on the right are all overlapping or eclipsing with each other, so we call that the eclipse conformation. If you look at the relationship between these two structures, these two differ by a 60-degree rotation of the C-C bond. That is to say, I could take this, and let's just kind of label these things so we can see them. I'm going to take this northernmost hydrogen and spin it clockwise 60 degrees. So when I spin that clockwise 60 degrees, remember I go from, I go kind of halfway between the two groups of that dotted carbon. So now that purple carbon is sticking up and to the right in an eclipse conformation. Okay, when I do that though, I have to move all of the other hydrogen atoms that are attached to the dotted carbon. The circle stays fixed. It doesn't change. The circle carbon doesn't change. I could have rotated the circle carbon, but I would have to leave the dotted carbon fixed. So you could do either one, and you should be able to do either one. That's an important skill, is that we're able to kind of rotate, use Newman projections to do free rotation over carbon-carbon bonds. So we do a 60-degree rotation, and we go from the staggered conformation to the eclipse conformation. Let's keep going. Let's rotate this less stable eclipse conformation another 60 degrees. I've got this kind of swooping curly arrow to show rotation, but I should be more specific. This is a 60-degree rotation. and it's clockwise, and it's really of the dot carbon in the clockwise direction. My arrows show that though in the structure above, where I'm kind of spinning this way around. Okay, so I'm rotating 60 degrees. What does my Newman projection look like? Well, I have a dot with a circle around it. The back carbon stays put, so those hydrogens stay in place. But it's the front carbon that now switches from vertical down to vertical up. Specifically, if we're tracking the progress of our purple hydrogen, it is now down and to the right. If you look at this final structure, it's a staggered conformation again. And just like the original structure, our staggered conformation is more stable. That's a lot of arrows. Our staggered conformation is more stable. Sorry, I guess I need it. So the staggered conformation that we started with the purple atom that was up top, now looks like we have another staggered conformation. We're tracking the progress of the purple atom, but it hasn't, the structure's the same. A hydrogen's a hydrogen, right? Assuming there's no isotope effects. So we've drawn the same structure twice. Staggered, 60-degree rotation gives an eclipse structure. Another 60-degree rotation gives a staggered structure. Okay, let's actually plot that graphically. There are some things we can know that are really helpful to us. The eclipsed conformation is less stable, and that's how we started the lecture. And it's less stable by 2.9 kilocalories or kcals for every mole of eclipse conformations that we generate from a staggered conformation. So if we graph this, and what I'm going to do is I'm going to use this vague x-axis called rotation progress. And I'm saying that if we start with a staggered conformation and we rotate, we're going to go up in energy to an eclipsed conformation. In particular, I'm going to set the y-axis so that the staggered conformation is at 0, and this is going to be energy per mole, and we'll just specify that it's kilocalories. And we go up to the y-axis now is going to be 2.9 kilocalories per mole for my eclipse conformation. And so what is this dotted line? This dotted line represents a 60-degree rotation. What I can do is I can continue on with another 60-degree rotation, and that brings me down to another staggered conformation. So we're going to have a second staggered conformation by way of another 60-degree rotation. And if you remember 120 degrees from our first lecture on conformational isomers, 120 degrees kind of interconverted, made the structures look the same. We split the circle in thirds. If we had a vertical substituent up, it stayed up after 120 degrees. Well, it didn't stay up, it moved, but there was another thing to replace it that was also vertical. Well, look at this graph. What if I do a few tweaks to this graph? Maybe I replace reaction progress with rotation progress with reaction coordinate. Then instead of having these dotted lines, I make like a valley at the staggered conformation, go up to a hill at the eclipse conformation, and then go back down into a valley for the staggered conformation again. If you look at this, this is a, the red curve is a potential energy surface where the y-axis is delta G, or the change in free energy. We started at 0, we went up 2.9 kcals. And then our rotation progress is the same as our reaction coordinate, you know, that arbitrary x-axis where we're just changing the arrangements of atoms. So this is an energy diagram for free rotation. So 120-degree free rotation is shown by this energy diagram. And there's some really interesting things that emerge. If you look at this energy diagram, the eclipse state is really a transition state. It's really just a transition state. So the eclipse conformation is a transition state for some sort of chemical process. What is that chemical process? Well, it's free rotation over a sigma bond. That's kind of interesting. We can plot this all energetically, and we could understand it using Newman projections. So that was for 120 degrees. What does the energy diagram look like for 360 degrees rotation? Well, let's go ahead and plot that. So we're going to do another energy diagram. Excuse me. So I'm going to go ahead and label this as reaction coordinate. It's not really a chemical reaction or a changing of transformation of matter. It's a rotation progress, but reaction coordinate kind of depicts a change in atoms, and it does like to, anytime we can, we like to incorporate free rotation if it's meaningful in an energy diagram. So I don't think it's a bad idea. Well, for 360 degrees, we need to start staggered. I like to start staggered because, I mean, why not? It's a low energy state. We need to do a 60-degree rotation, then a 60-degree rotation, and this is exactly what I drew on the last page. So we go from staggered or an S conformation to an eclipsed or E conformation, back to staggered. Then if we do 60 degrees again, we're going to go to eclipsed, then staggered, then eclipsed. So we're at 60, 120, 180, 200, 60 again is 240, and then 60 again. Do I have that right? Should be 300. Oh yeah, 300. And then 60 again is 360. So it's over and over again. It's just kind of going from staggered to eclipsed to staggered to eclipsed to staggered to eclipsed. And the change in energy is consistent. It's set to 2.9 kcals. But so we have here, we have two intermediates. We have three transition states to get us from start to finish. And it's kind of helpful if I, hey Logan, if I have a molecule like this where I've got two different color balls, so it looks like an orange and a blue ball to my eyes, what I'm going to do is I'm going to start them eclipsed, but they're pointing in the opposite direction. And then we can actually track this. So this is our first 60-degree rotation, our second 60-degree rotation, our third 60-degree rotation, which puts eclipsed where the two groups are right on top of each other. And let's just see, after 3 60-degree rotations, are we at an eclipse conformation? So there's 1, 2, 3, and we're at an eclipse conformation. So we're tracking pretty well. 4, 5, 6, back to the original structure. Or I'll call them the same. And that's not really a big deal. I mean, if you go 360 degrees in a concentric circle, you're going to land where you started. You try to be quiet there, buddy? Sure. Thanks. Okay. So we have an energy diagram for a 360 transition. It's actually kind of helpful, right, to look at this, this sort of depiction. Is there a real molecule where the two groups at the end of the chain are different from each other, so we could actually track the progress? it's kind of boring when they're all hydrogens, right? Because this is the same as this if the orange and the blue and the white dots are all the same, right? They're the same structure. There's a free rotation event that's happened, but because the atoms are the same, we can't tell the difference between the two structures. Well, there is an example where we could make those two groups different, and that's called the butane. I mean, a good example of that is just butane. So the conformational isomers of butane. So butane, recall, is a straight chain hydrocarbon with 4 carbons attached. So what we want to do is we want to draw that molecule and we want to analyze this bond. So we're analyzing that bond. And what that means is that we're going to start with some more complicated Newman projections. So I'm going to have a dot with a circle around it. And let's say, and so what I'm saying is we're going to get to a structure like this. And let's have these 2 orange and blue dots pointing in opposite direction. Now, what are the orange and blue dots? Well, maybe it'd be better if I made them both green, because in this particular example, they're both going to be CH3s or methyl groups. I realize I should maybe add black dots to this, but then it's just a lot of black dots. I really want to track the difference between these. So I've got green dots now, so that we can tell that they're the same. Now, what I'm saying is that the green dots represent the carbons at the ends of my butane chain. They are CH3s, it's just that adding a bunch of CH3s would be kind of annoying. We could write out CH3 if we wanted to. And let's do that. And let's draw this conformation to start. So this conformation, I'll draw here. Our front carbon is pointing down, front vertical is pointing down, and that is a CH3. And the back carbon is pointing up, which is a CH3. And just for clarity, let's actually write CH3 here. We should know this at this point, that the bond line structure butane has CH3s at the end. So we were going to go down to a CH3. And again, that was a green, that was my green dot. And then up to a CH3. And that was my other green dot. And the white dots are hydrogen atoms, or the white balls on our model, excuse me. And we should include those hydrogen atoms in our staggered conformation of butane. Well, this is a really important structure of butane. This is called anti-butane. Anti. And the reason why is because the groups are opposite of each other. The groups, and by groups I mean the green dots, are opposite of each other. Okay, what I want to do now is a 60-degree rotation. Now, which way should we go? I like keeping the, let's rotate the back carbon 60 degrees. We'll make it interesting. Okay, so we're going to rotate the back carbon, excuse me, the back carbon 60 degrees. That's going to go from a staggered conformation to an eclipse conformation. And I should also mention the direction I'm going. I usually go clockwise. You could go counterclockwise if you wanted to. So what I'm getting at is that we're taking this molecule, we're keeping the front atom fixed, and then we're rotating 60 degrees clockwise. Hopefully that's clockwise on your camera. It looks clockwise to me, but maybe it's flipping it again. Okay, anyway, so dot with a circle around it. We're going to, what's more important is what happens on the piece of paper. The things that are connected to the dot are not going to change in this instant because I'm rotating the back carbons. So I have a CH3 or a methyl group rotating 60 degrees in the back, and now it's pointing up and to the right because I was rotating counterclockwise. To maintain 120 degrees, I need to position the groups like this. So they're truly on top of each other, but it's harder to see, right? It's a little bit harder to see. So we're going to draw it askewed and get to an eclipse conformation. So I'm going to call this eclipsed 1. So we're going to rotate 60 degrees again. We're going to go in the same direction where we're going the back carbon atom 60 degrees. And that's always fun because we're going to get to a staggered conformation. So the front groups again remain the same, but the back groups change. And so now they're staggering or splitting the front, the groups attached to the front carbon atom. And so we have a structure that looks like this. This is an important structure. It is staggered. And maybe I would have called the anti-structure the staggered one. It is staggered, but this structure has a special name, and it's called gauche or gauche, depending on who you talk to. Gauche or gauche. So there's some important terms that are emerging here that we need to take away from this lecture, and that is the idea of anti and gauche or gauche. What I want you to notice about the anti and the gauche structures is that they're both staggered conformations. The difference is that now the CH3s are closer to one another. They're closer to one another. In fact, it kind of looks like they're 60 degrees from one another. Now, they're not attached to the same carbon, so they're not 60 degrees. That angle that you're thinking about, which I could highlight, is called the dihedral angle. The dihedral angle for this molecule has the CH3 groups now 60 degrees separated. And I can sketch that out before the lecture's over, but that's not something to worry about too strongly. But anyway, we're at the gauche conformation. By adding the two groups, we can tell the difference now between this structure and this structure. While they're both staggered conformations, now the green balls are closer to each other. Now the CH3s are closer to each other, and we'll see in a second that they have different energies. What I'm going to do now is I'm going to rotate the gauche gauche conformation another 60 degrees from the back. So let's rotate 60 degrees again. And I think I want to make this arrow just a different color so you can see the how close those CH3 groups are. Anyway, back to the black pen. We're going to now rotate 60 degrees, and I hate to say unfortunately, but we are going to get to another eclipse conformation. Front stays the same. CH3 pointed down, up and to the right, up and to the left with hydrogens. Now we're going to have groups here, here, and here. This structure is really crowded because the CH3s are directly on top of each other now. CH3s are directly on top of each other now. And this structure was called, I want to make sure I maintain the right names. So this is called the Syn Conformation. The Syn Conformation, S-Y-N, not S-I-N. We're not, this isn't a biblical discussion. So S-Y-N, and in the Syn Conformation, the big, in quotes, groups are overlapped. Or you could say the CH3s are syn to each other. Whereas before you could say in the first conformation we looked at that was staggered, where the CH3s were on opposite sides, you would say the CH3s are anti to each other. Okay, so we have syn and we have anti and we have gauche. These are important terms. The rest I think is mostly going to be staggered and eclipsed. So that's a problematic conformation to have the big groups overlapping like that. Let's get out of there as quickly as we can. We'll do another 60-degree rotation. So I'm going to rotate again the back only. 60 degrees. Sigh of relief, we can get to another staggered conformation. Another staggered conformation. Now the CH3 and the back carbon is pointing down and to the left. The rest are just H's, and we're at staggered again. What I want to point out about this conformation is this staggered conformation has the CH3 groups closer to each other than we would see for the anti-conformation. This is another gauche or gauche conformation. So being able to recognize gauche conformations and distinguish them from anti-conformations will be important. Let's keep on going though. Let's keep rotating 60 degrees again. I'm going to need a lot more space than that. So 60 degrees, the back only gets us to an eclipse conformation. We only have to do this 2 more times before we're at 360. So H, H, CH3, CH3, and H, H, CH3. Okay. This conformation is sort of a run-of-the-mill eclipse conformation. And so this is eclipsed 3. There's no special terms for it. We don't have big groups overlapping, so it's not Syn, and the other terms only apply to staggered conformations. But if we do a 60-degree rotation again, we've completed a 360-degree circle, rotating the back this time, clockwise in every case. Puts our CH3 up on the circle, CH3 on the dot down. The dot remained the same during the entirety of that free rotation process, and we're back to, put that in parentheses, because this isn't a new conformation. We've seen this one before. It's the one that we started with, back to staggered. And this is in particular, I should clarify, we're back to anti. The parentheses should go around here. I'm like wordsmithing my lecture notes in the midst of a lecture. Okay, we're back to anti again. So we saw a number of conformations. They were all different to some degree this time, except for the 2 anti-conformations. Some looked very similar, but they were mirror images. That's an important point for later. But we saw a lot of differences now between the conformations, as opposed to just going from staggered to eclipse to staggered to eclipse to staggered to eclipse to staggered to eclipse. Things are going to be a bit different when we look at the energetics. Let's go ahead and break down the important conformational isomers that emerged from this discussion. So the important isomers were, firstly, the anti-conformational isomer. The anti-conformational isomer. Okay, in the anti-conformational isomer, the big groups are opposite and in plane with each other. We call this the anti-conformation. And we say that the groups are anti-periplanar, where we have same plane is what periplanar means, and then anti means opposite. Okay, so they form in the same plane, but they're on opposite sides of the molecule. We may also call this periplanar or coplanar. Another term that we would look at, another important conformation, was the Gauche conformation. The Gauche conformation is a staggered conformation where 2 groups have a 60-degree dihedral angle. Now, dihedral is not anything too complicated, and we're not going to have to kind of predict dihedral angles, but all it's saying is that if you've got something attached to the front and something attached to the back carbon, they may appear based on perspective to be only 60 degrees separated. But in reality, that 60 degrees extends across 4 atoms. So we would have C, C, and then let's put a star here, a star here. So I think I highlighted it yellow before, but this apparent 60 degrees actually looks like this when we convert to a seesaw structure. So that's the Gauche conformation. And really a Gauche conformation or a Gauche interaction describes kind of 2 groups that have a 60-degree dihedral angle when bonded in a sigma bonding system. So this is the Gauche conformation. And then the last one we saw was the Syn conformation. The Syn conformation has the 2 big groups, Syn, and I like to use the word coplanar here, Syn coplanar, or on the same side and overlapping. Same side and overlapping. Okay, what's kind of interesting about all of this is when we look at the energetics of these systems. So the energetics are such that we can start to see a new topic emerge that we'll talk about quite a bit, especially in the next module, and that is steric hindrance. And steric hindrance says that when large groups are placed close in proximity, the potential energy of the system increases. So when we put big things together, the energy of the system increases. That's what this is saying. That's an important term that we'll talk about quite a bit. So with this in mind, what we have here is we have some energetics, and it turns out that, let's space it this way. So if we have energy here, and we have high energy and low energy, the lowest energy state is going to be that state where the big groups were farther away, because when they're farther away, they're not crashing into each other. They don't impose as much steric hindrance. And so they're going to be lower in energy. This is our anti-conformation. The higher energy system is going to be our eclipse conformation, and that is going to be, the highest one is going to be the Syn conformation. We've got the 2 big groups directly over top of each other. In between here, we're going to see the other conformations emerge, and we're going to see that the eclipse structures, hey buddy, don't worry about it. The eclipse structures are higher in energy than the anti-conformation, but not as high as the Syn conformation, and then splitting between the non-Syn eclipse conformations and the anti-conformation are the Gauche conformations. So it goes anti, Gauche, eclipsed, Syn. And with this in mind, we can start to sketch out an energy diagram for this particular system. And to do that, we should assign some energetics. So the Syn conformation, before we saw eclipse conformations at about 2.9 kcals per mole, but Syn is really high in energy. It's 4.9 kcals per mole. Eclipsed is 3.6 kcals per mole. Gauche is higher in energy than the anti. The anti we set to 0. We just say, okay, let's set that to 0. Everything else is relative to it. The gauche is higher in energy than the anti at 0.9 kcals. But remember that the gauche is still a staggered conformation. And if it's a staggered conformation, it's not going to be as high in energy as 2.9 kcals, which we saw for the eclipse conformation of ethane. It's going to be lower in energy. Now, the things you need to know are only this in terms of numbers. But I also want you to know this, this, and this. So I want you to know the relative ranking of the various energy states, or the various conformational states, anti-Gauche, eclipsed in general, and Syn. Okay, I want you to know though, but in terms of what numbers do you need to know? The number that I'd really like you to know is that 0.9 kcals per mole is the typical energy for a Gauche interaction. So let's go ahead and draw the energy diagram then. Give ourselves a lot of space. So we're going to have reaction coordinate to describe the free rotation, and we're going to do a 360-degree rotation of butane. We're going to focus only on that central carbon-carbon atom. Central CC bond only. Okay. Put delta G relative to our starting state, which is going to be set to 0. And I know that it looks like the y-axis hits 0 down in the horizontal line, but that makes it really hard to draw. So, you know, this could be like -2 or something. I don't know. It doesn't matter. The point is we've got our 0 point defined. And what was 0 kcals per mole? That was the anti-conformation. Then we're going to do a 60-degree rotation up to an eclipse conformation, which is at 3.6 kcals. So that was eclipsed 1. Then we're going to go down in energy, but not all the way down to 0. That's what we did for ethane, but we're going to stop down here at 0.9 kcals to land onto a Gauche conformation. And then back up in energy to an eclipsed. But is it the same as eclipse 1? No, it's much higher in energy as we enter the energetics of, I think I said 4.9 for the Syn conformation. And then we're going to just kind of do, I like the term mirror image, because from Syn we go to another Gauche conformation, back up to an eclipsed. And eclipse 3 is the mirror image of eclipsed 1. They have the same energy, they're degenerate, but they are different conformations. And we'll talk about that during the exam 4 or 5 material, I can't remember. But from eclipse 3, we get back to where we started. The only duplicate conformation on this is the anti-conformation, which is tied with the original anti-conformation at 0. And if we want to, sometimes it's helpful to draw these dashed lines, because in the context of conformations, we see that we have 60 degrees, 60 degrees, 60 degrees, just like with ethane. And it is sometimes helpful to think about the potential energy surface with the curves. We can see this overall shape. There's some symmetry to it, that sort of thing. But that is the energies, the potential energy surface and the energy diagram for CC rotation at the 4-butane. And what's the rate determining step for a full 360-degree rotation? The rate determining step, the highest transition state energy, would be the Syn defined by the Syn conformation, and it's the conversion of a Gauche conformation to a Gauche conformation. So using Newman projections, we can see a lot of detail about free rotation over carbon-carbon bonds. And this was just a simple molecule butane. All we did was we took our simplest example, ethane, and added 2 groups to it, groups on either side of the caps of the chain, and then we did our free rotation. It allowed us to distinguish between the left and the right side, which really unveiled a lot of interesting things. We saw conformations that were once the same. Staggered conformations start to look different as we had anti and Gauche conformations emerge. And then we saw that Syn could really increase the energy quite a bit and distinguish itself from the other eclipse conformations. So that'll do it for module 2. We'll look a lot more at conformational isomers in larger systems, but hopefully this will give us the baseline toolbox that we need to start to analyze these things in more detail.